Echolocation, or in other words, using sound to locate an object. Bats have it, boats have it, even some humans have developed the ability to use echolocation. But what is echolocation? Echolocation is where sound is used to see an object. This is done by making a sound, and then when the sound comes into contact with an object, it bounces back from the object, and then, in the case of an animal, we use their ears to locate which direction the sound bounced from. But how does this happen? To demonstrate echolocation, I'll be using this distance sensor which I have here, which is essentially a 2D echolocator. The distance sensor has 4 pins, a power pin, or brackets VCC, a negative pin, or ground, a trigger pin, which is short for trig, and an echo pin. How this works is important, as this is how most echolocators work. When we want to measure the distance of something, a signal is sent to the trigger pin, which then the sensor will output a sound at 40,000 Hz, which is double the hertz a normal human can hear, and it outputs this signal for around 10 microseconds. Then the echo pin will essentially send a signal back to the microcontroller here, and this will count how long the echo pin has been on. When the sound hits something and then returns, echo pin will deactivate, no longer sending a signal back to the microcontroller, and so will stop the counting. Then, doing speed multiplied by time, we get the distance the object is away, where the time is how long the echo pin was active and the speed is the speed of sound. As you can see here, I have an object, which is my multimeter, which is 10 centimeters away from the distance sensor, which is here. And you can see this as shown by the ruler. And by reading from the distance sensor, for which I have on the screen, you can see it is 10 centimeters. When I move it closer to the sensor, as shown by the ruler and the screen, you can see that it does get the numbers go down, because the time it takes for the sound to rebound off the object is quicker because it's closer to the actual thing it's rebounding off. And with this distance and time, we can work out the speed of sound. At 10 centimeters away from an object, the speed it takes for the sound to get from the trigger, bounce off an object, and rebound into the echo pin is around 593 milliseconds, or 0.00053 seconds. To get the speed of sound, we use velocity equals distance times time, where distance equals 0.1 meters as 10 centimeters, and time is 0.000593 seconds. Or in short form, distance equals 0.1 meters and time equals 0.0593 seconds, which means that velocity equals 0.1 divided by 0.000593, which means velocity is 168.634. Then multiply this by 2, as the sound has to travel 10 centimeters to get to the object, and then another 10 to rebound back, which means velocity equals 168.634 times 2, which means that velocity equals 337.268 milliseconds to the power of negative 1, which, being that the speed of sound is actually 343 meters per second, also that being 6 meters off is pretty good. Well, this is only with the distance sensor, which is in 2D, so how is echolocation using something that is 3D? Well, it's the same logic, having something to make a sound with something counting how long it takes, but the receiver is essentially 2 receivers. This makes an important difference, as you can determine the direction of the sound with 2 ears, but it's very hard with 1. We as people can hear sound coming from a direction by how loud it is in one of the ears, but what is the science behind it? It all has to do with triangles. Let's bring up my distance sensor again. Let's say I have another one here. So when the sound is broadcasted from one of the distance sensors, the time it takes to get to each echo pin can determine whether the object is using the distance from both of these echo pins and using triangles. As you can see here, one of the distance sensors is acting as a trigger, while the echo on both of them are going. We can see that the left distance sensor reads a distance of 38 centimeters, while the right one reads 28 centimeters, with both receivers being 18 centimeters apart. With this knowledge, we can find the angles that the sensors read from. But to get an angle and a distance from the source requires some triangular thinking. We essentially need to record the length and distance of the red line. To start, we work out the angles of all the angles in the blue triangle. To do this, we use the law of cosines, where we know 3 sides. We know side A, which is 38 centimeters, side B, which is 28 centimeters, and side C, which is 18 centimeters. And with this knowledge, we can use the rule of cosine, where cosine C equals A squared plus B squared minus C squared divided by 2AB. So if we substitute this in, this gets cosine C equals 38 squared plus 28 squared minus 18 squared, which is all in brackets, divided by 2 times 38 times 28. Which means that cosine C equals a starting bracket 1444 plus 784 minus 324 in bracket, and we divide that by 2128. Which is essentially cosine C equals 1904 divided by 2128, which means that, and then we do cosine to the power negative 1, which is 1904 divided by 2128, which means that C equals 26.52 degrees. This means we can also find angle A, where cosine A equals 28 squared plus 18 squared minus 38 squared divided by 2 times 28 times 18, which means that cosine A equals 784 plus 324 minus 1444 divided by 1008, which means that cosine A equals negative 336 divided by 1008, because that cosine to the power negative 1 minus, in brackets, negative 1/3, which equals 109.47 degrees. This means that we can work out angle B because of the angles in a triangle, where A plus angle B plus angle C equals 180 degrees. So 180 minus 109.47 minus 26.52 equals B, where B equals 44.01 degrees. With this knowledge, we could draw up another triangle where the trigger sees from, essentially, and from one of the receivers. We can work out the red line by, again, using the cosine rule, where A squared equals B squared plus C squared minus 2BC times cosine A, where A squared is essentially the red line, where A squared equals 9 squared plus 28 squared minus 2 times 9 times 28 times cosine 109.47, where, and again, A squared equals 865 minus 504 times negative 1/3, where A squared equals 1032.9899, where, and then again, A squared equals 32.1402. And by working at the angle that the trigger sound rebounded off, comparing it to being straight on, like as you can see, where cosine A equals 32.14 squared plus 18 squared minus 28 squared divided by 2 times 29.4 times 18, where cosine A equals 1032.14 plus 324 minus 784 divided by 1058.4. And then again, cosine A equals 572.14 divided by 1058.4. And then we do cosine negative 1, which is, and then in brackets, 572.14 divided by 1058.4, which means that angle A is 57.277 degrees. And from this, where north is forward, it is on a bearing of 327.278 degrees, meaning that the object, which is a multimeter, is 32.14 centimeters away from the trigger at a bearing of 327.28 degrees. Though, the problem being, the brain of an animal cannot calculate the specific degree at which the sound has bounced off, so they use their ears to get a general direction of the sound, just like a sound that we normally hear. Why does sound bounce off an object? This is because sound travels as a pressure wave through air, with the sound carried through the air molecules colliding with other molecules that are in front of it, making the sound travel. These pressure waves travel as waves, but travel in longitudinal or compression waves. But these are hard to visualize, so they are drawn in transverse waves to make it easier to read. These transverse waves tell us a number of things. It tells us the volume and it tells us the pitch. If we take a single loop of wave, the longer it gets, and the shorter it gets, the higher the pitch. If the wave was to increase in size, it would increase in volume, but if it was to decrease in size, it would be quieter. Because of how sound waves travel, when the sound wave hits an object, some of the sound will get absorbed while some gets rebounded back. It's because sound essentially is a vibration of atoms, and sound can travel easily through air, but when it comes into contact with an object, it cannot penetrate very far, and so the sound wave is turned back on itself. This creates an echo that the receiver can hear, and the further away the object is, the longer it takes for the sound to travel, rebound, and travel back. When I talk about 40,000 Hertz, what I mean is the frequency that the sound is. And frequency is measured in Hertz, which is essentially the size of the sound wave. We can calculate frequency by the following equation, where frequency equals 1 divided by t, where f is the frequency and time is the time it takes for a wave to complete one wave cycle. So if we use the distance sensor again, if the distance sensor outputs 40,000 Hertz, then that would mean that 40,000 equals 1 divided by t. So we can use this to be t equals 1 over 40,000, where t equals 0.000025. This means that it takes 0.000025 seconds for a full wave at 40,000 Hertz to pass a point. The important part to remember though is that this is a change in size, where the gaps between the waves are closer to each other, and this is not a change in speed. So that with all this knowledge, we can draw up a diagram of what happens. Let's say that a bat wants to eat something. It uses echolocation to detect what objects are in front. This essentially means that the bat makes a sound at around 40,000 Hertz, and this sound will travel until it hits something and the sound is rebounded back. Using its ears, the bat can work out where the sound came from and how fast the sound came back, and with this, the bat can work out where the object is. And that is echolocation.